Welcome back to the deep dive. Today we are stripping away the noise, the pop culture, and the general trivia. We're getting incredibly specific.
And honestly, a little bit intense.
A little bit, yeah. If you are tuning in right now, you probably aren't just looking for a casual conversation. You are likely a postgraduate student, probably a resident deep in the trenches, and you have a very specific, very intimidating hurdle in front of you. The Gujarat University MD Anesthesiology exams.
That is exactly the target audience today. And if that's you, I know what you're feeling. You have the theory papers, which are grueling, but then you have the practicals, the viva voce.
The viva.
And there's one station in that viva that is, well, it's absolutely non-negotiable. You will be standing right next to a piece of equipment that defines your specialty, the Boyles anesthesia machine.
Exactly. So consider this your specialized coaching session. I'm here to ask the questions that you, the candidate, might be too afraid to ask. And our expert here is going to play the role of the senior MD faculty mentor.
That's the plan.
We aren't just going to list parts. We are going to teach you how to structure a high-yield answer that gets you the marks and, more importantly, ensures you don't endanger a patient.
We have to be rigorous. This isn't just about plumbing, it's about life support. We've pulled from the absolute heavyweights for this deep dive. Miller's Anesthesia, Morgan and Mikhail.
The classic.
The Objective Anesthesia Review, and, specifically for our listeners in India, resources like Kaushik Jothanath, which are really the gold standard for local exam patterns.
The mission is simple. We are going to take this complex beast of pneumatic engineering and turn it into a structured, flawless exam answer. By the end of this, you should be able to visualize the schematic for your theory paper.
Dodge the classic Viva traps.
And mentally perform a machine check that ensures patient safety. So let's dive into Part A, Introduction.
Right. Let's set the stage. You are in the exam hall. You get that dreaded 20-marker question. Describe the safety features and working principles of the anesthesia machine.
Or you're in the Viva, and the examiner just points at the workstation and says, "Tell me about this."
Exactly. Tell me what this is. So how do you begin?
I think most people would just say, it's a Boyles machine.
And that is where you lose the first impression marks. You need a precise definition. Right away, you must define it as a continuous flow anesthetic machine.
Okay, so lead with that phrase.
Always. Historically, yes, it's derived from the original 1917 design by H.E.G. Boyle and the British Oxygen Company, you can mention that. But in the modern context, you have to focus on the function.
Which is?
It's a precision device designed to receive compressed gases, reduce their pressure to a safe working level, mix them accurately with potent anesthetic vapors, and then deliver them to the patient via a breathing circuit.
I like that structure. Receive, reduce, mix, deliver. It sounds simple.
But the engineering behind it is what keeps the patient alive, right?
Right.
So you have to emphasize the safety context in your introduction.
Yeah.
Modern workstations are, for all intents and purposes, life support systems. The exam focus is always on control. If you can't control the flow, the pressure, and the concentration, well, you are essentially poisoning the patient.
And it's important to mention that even with all the new screens and ventilators, the core is still the same.
That's a very good point. You should mention in your exam intro that while modern machines are complex workstations, the core pneumatic principles remain tied to that original Boyles concept.
And these questions, they don't just come in one flavor, do they?
Not at all. You might get the long question, the 20-marker, on the whole machine. Or you could get short notes on specific bits, like the pin index safety system or hypoxic guard.
And the Viva?
The Viva is almost guaranteed. They will ask you to touch the part you were talking about. Show me the bobbin. Trace the gas flow. Where is the emergency flush? You need to know the geography of the machine as well as the physics.
Okay, that sets the scene perfectly. Let's move to Part B, Basic Principles. This seems to be the mental framework we need before we even touch a knob or a dial.
This is a very high-yield concept. I can't stress this enough. If you are asked to draw the machine, and you will be, you don't draw a picture of a cart with wheels and drawers.
You draw a schematic.
You draw a schematic based on pressure. You must divide the machine into 3 distinct pressure systems: high, intermediate, and low. This is the absolute foundation of your answer.
Okay, this is the skeleton. Let's unpack them one by one, starting with the high-pressure system.
So the high-pressure system is actually physically very small. It consists strictly of the parts that handle the full raw force of the cylinder.
So it's just the cylinder and the connector?
Pretty much. You have the cylinder itself, the hanger yoke where you attach it, and the high-pressure side of the first-stage regulator. That's it.
And when we say high pressure, we aren't kidding.
No, not at all. We are talking about 2,000 pounds per square inch. or psi, for a full oxygen cylinder. That's roughly 137 bar. It is a massive amount of potential energy,
which you absolutely cannot deliver to a patient.
If you release that directly into a patient's lungs or even into the flowmeters, you would blow the machine apart and cause catastrophic barotrauma. The sole purpose of this system is to contain that bomb and feed it into the regulator.
Okay, which brings us to the intermediate pressure system.
This is the bridge. It starts immediately after that first pressure regulator. The regulator steps to that terrifying 2,000 psi down to a much more manageable, stable working pressure.
How much are we talking?
Usually around 45 to 60 psi, roughly 3 to 4 bar. This system includes the pipeline inlets coming from the wall, which also arrive at this pressure, and the plumbing for the oxygen flush valve. It runs all the way up to the flow control valves.
So the knobs we turn on the front of the machine, they're the boundary line.
Exactly. The flow control valves, the knobs for oxygen, nitrous, air, they are the gateway. Everything upstream of those knobs is intermediate pressure.
And everything downstream is?
The low-pressure system.
Let's talk about that low-pressure system. Why is this distinction, this three-part model, so critical for an anesthetist to understand?
This is the most vulnerable part of the machine. The low-pressure system starts at the flow control valves. It goes through those delicate glass flowmeter tubes, through the vaporizer manifold, and it ends at the common gas outlet, or CGO. The pressure here is very, very low, just slightly above atmospheric pressure.
And why is that a risk? I would think high pressure is the risk.
Well, it's about leaks. If you have a leak in the high-pressure system, it's loud. You hear a hiss. You lose gas, sure, but as long as you have supply, the patient is still getting what they need. But a leak in the low-pressure system, it's silent. And because it is downstream of all your gauges and your safety devices, the machine doesn't even know what's happening.
So you could have a crack in a flow tube.
Exactly. Or a loose O-ring on a vaporizer. You might be delivering less gas than you think you are, or even worse, you could be in training room air. This can create a hypoxic mixture without any alarm going off.
That is a terrifying thought. The machine's dial says 100% oxygen, but the patient is actually getting a mix of oxygen and a room air because of a tiny silent crack in the glass.
That is precisely the danger. And that is why understanding these three zones isn't just for the exam diagram. It's for understanding why the low-pressure leak test is the single most important part of your morning check.
Okay, I think that's crystal clear. Let's get into the hardware then. Part C, components of Boyles' machine. We'll start at the source, the gas supply system.
Specifically, the cylinders. In the exam, this is Viva Territory 101. You will see Type E cylinders on the back of the machine. You need to know the data points for these cold.
Let's drill the numbers. Oxygen first. What do we need to know?
Okay, the oxygen cylinder body is made of molybdenum steel. This specific alloy is used to handle that immense pressure while keeping the weight manageable so you can actually lift it.
And its capacity.
For an E-type cylinder, the internal water capacity is roughly 4.7 liters, which, when filled, translates to about 660 to 680 liters of gaseous oxygen. And the pressure, when full, is, as we said, roughly 2,000 psi.
And the physics principle here. How do we know how much is left? This is important.
It is. Oxygen is a compressed gas. It doesn't liquefy at room temperature in these cylinders. So it obeys Boyle's law. The pressure is directly proportional to the volume.
So it's linear.
Perfectly linear. If your gauge reads 1,000 psi, which is half of 2,000, you have exactly half the gas left.
Yeah.
You can calculate down to the minute how much oxygen you have left based on your flow rate. Very predictable.
Now let's contrast that with the classic exam favorite, the nitrous oxide cylinder.
Nitrous oxide. This is the trap. The critical temperature of nitrous oxide is 36.5 degrees Celsius.
So just above body temperature.
Right. And since room temperature in an air-conditioned OT is usually well below that, nitrous exists as a liquid under pressure inside the cylinder. It's in a liquid-gas equilibrium.
What are the numbers for nitrous?
A full E-type nitrous cylinder holds about 1,590 liters of gas, much more than oxygen. The pressure, however, is much lower, around 745 psi.
But here's the catch, right?
Here's the catch. As you open the valve and use the gas, the liquid nitrous boils off to replace the gas you just used. This process restores the pressure right back to 745 psi.
So the gauge basically lies to you.
It doesn't lie, but it misleads you, which is just as dangerous. The gauge will read full 745 psi continuously until every single drop of liquid has evaporated. You could have 90% liquid left, or you could have 1% liquid left. The gauge will look exactly the same.
And then it just drops off a cliff.
It falls off a cliff. Only when the liquid is completely gone does the pressures start to drop. And by that point, you have practically nothing left. You're running on fumes.
So if the examiner asks, how do you measure the contents of a nitrous oxide cylinder? The answer is not, look at the gauge.
No. The only correct answer is by weight. The tare weight, which is the empty weight, is stamped on the neck of the cylinder. You weigh the cylinder, you subtract the tare weight, and the remainder is the weight of the nitrous oxide. You cannot rely on the pressure gauge.
Okay, that's a huge point. Now let's talk about cylinder identification. In a crisis, you don't have time to read fine print. You need to know what you are grabbing.
Color coding is your first line of defense. And here, I must stress the regional difference. If you are sitting the Gujarat University exam, you are following the ISO-British standards, which India uses.
Okay.
In this system, oxygen cylinders have a black body with white shoulders.
Not green. A lot of people think green.
No, green is the United States standard. If you walk into an Indian exam and say green cylinder, the examiner will assume you learned anesthesia from watching American TV shows, not from working in the ward. Be specific.
Yeah.
Black body, white shoulders.
Got it. And nitrous oxide.
That's French blue.
Okay, what about air?
A gray body with black and white quarters on the shoulder. This quartered look is very distinctive and easy to spot.
But paint can chip, or the lights might be dim. We need a mechanical failsafe. And that brings us to the Pin Index Safety System, or PISS.
Absolutely. PISS is a brilliant, simple mechanical method to prevent attaching the wrong cylinder to the wrong yoke. It consists of 2 pins on the yoke of the machine.
And 2 holes on the cylinder valve.
Exactly. And the position of these pins is unique for each medical gas.
We need to memorize the indices, don't we?
I'm afraid so.
Uh-huh.
This is just rote learning, but it's essential. For oxygen, the pin positions are 2 and 5.
2 and 5.
For nitrous oxide, it's 3 and 5. For air, it's 1 and 5. And for Entonox, which is the 50-50 mix, it's position 7.
Just remember, oxygen is 2,5. That's the one that keeps the patient alive. Is there another part of the connection we need to mention?
Yes, the Bodox seal. It's a small, metal-bonded rubber washer. It sits between the cylinder valve and the yoke. Without it, you cannot get a gas-tight seal.
And if you hear a massive leak when you open the cylinder,
the first thing you check is the Bodox seal. It is probably missing or crushed.
All right, let's move downstream to the pressure regulators. We mentioned they drop the pressure, but there is a nuance about why they drop it to specifically around 45 psi.
This is a beautiful piece of passive safety engineering. The hospital pipeline supply, the gas coming from the wall, usually runs at about 50 to 55 psi. The regulators on the machine are deliberately set to reduce cylinder pressure to a slightly lower level, around 45 psi.
Why the intentional difference? What does that do?
It creates a pressure gradient. Since the pipeline pressure at 55 psi is higher than the regulated cylinder pressure at 45 psi, the machine will preferentially draw gas from the pipeline. It actually pushes the cylinder check valve closed.
So even if you forget and leave the cylinder open,
the machine won't drain it, not as long as the pipeline is working. It saves your backup for when you really truly need it. It's an economy and a safety feature rolled into one.
That brings us nicely to the medical gas pipeline system, or MGPS. We have PISS for cylinders. What's the equivalent for the pipeline?
For the pipeline, we have the Diameter Index Safety System, or DIS. In some regions, you might also see NIST, which is non-interchangeable screw threads. The concept is the same. The diameter and the thread pitch of the hose connectors are unique to each gas. You physically cannot screw the oxygen hose into the nitrous wall outlet. The nut just won't fit.
And what about at the wall end itself, the part you plug in?
We typically use Schrader probes or quick couplers. These have a collar index, a specific geometric shape machined into the probe that will only fit into the correct gas outlet on the wall.
Okay, let's talk about the Flowmeters. The outline marks this as absolutely essential. I take it this is a big topic.
The Flowmeter assembly is the heart of the machine's accuracy. We use what's called a Thorpe tube design. The principle is a variable orifice, constant pressure system.
I remember struggling with the physics of this in class. Is the flow through it laminar or turbulent?
That's the million-dollar question, and the answer is it depends on the height of the bobbin. The tube itself is tapered. It's narrow at the bottom and gets wider at the top. Inside, you have a float, which we call a bobbin. At low flows, the bobbin is at the bottom. The annular space, that's the ring-shaped gap between the bobbin and the glass wall, is very narrow and long. It acts like a tube. In this state, the flow is laminar.
And laminar flow is governed by?
Viscosity. This is Poiseuille's law. So at low flows, the accuracy of your reading depends on the viscosity of the gas.
But as we crank up the flow,
The bobbin rises. The gap between it and the wall becomes wider and shorter relative to its width. Now that constriction acts less like a tube and more like an orifice. The flow becomes turbulent. And turbulent flow is governed by Graham's law, which depends on the density of the gas.
so low flow equals viscosity, high flow equals density.
Correct. And this is a really important concept because it explains why you can't just swap flow tubes between gases. A flow tube calibrated for helium, which has very low density, will be wildly inaccurate if you try to put nitrous, which is very dense, through it.
What about the bobbin itself? I've noticed it spins. Why does it do that?
Good observation. You'll notice small cuts or sloots on the rim of the bobbin. The gas stream hits these and makes the bobbin rotate. This is a visual confirmation for you, the anesthetist. If it's spinning, it's floating freely in the gas stream.
And if it's not spinning?
It might be touching the glass wall, stuck by static electricity or a bit of dirt, and that could give you a false reading.
Okay, and where do we read it? This is a classic Viva trap.
It is. If it's a standard flat-top bobbin, you read the top edge. If it's a ball bearing, which you sometimes see in auxiliary flowmeters, you read the center, the equator of the ball.
Now, the arrangement of the flowmeters. This is a crucial safety feature called the eager sequence, right?
This is absolutely non-negotiable. On any modern anesthesia machine, the oxygen flowmeter is always positioned downstream. That is, to the right closest to the vaporizers and the common gas outlet.
Walk us through the why using a disaster scenario. Let's make this really clear.
Okay, imagine you have 3 tubes in a line. Air, then nitrous, then oxygen. Scenario A, the dangerous way, let's say oxygen is on the left, upstream, and nitrous is on the right, downstream.
Okay.
If you get a crack in the nitrous tube, what happens? The oxygen flows through the manifold, it reaches that crack, and it leaks out into the room. The nitrous, which enters the manifold after the crack, continues on to the patient.
So you end up delivering almost pure nitrous.
You end up delivering a mixture that is dangerously rich in nitrous and poor in oxygen. You cause hypoxia.
Okay, now scenario B, the safe way, the eager sequence.
Oxygen is on the right, downstream, nitrous is on the left. Now, if the nitrous tube cracks, the nitrous leaks out. But the oxygen enters the system after that crack, so the patient gets less total gas volume, maybe less anesthesia.
But they're still getting oxygen.
They're still getting plenty of oxygen. The FiO2 is preserved. The eager sequence protects against hypoxic mixtures caused by leaks in the flowmeter assembly. It's a fundamental safety design.
Moving on to vaporizers. The outline calls this exam core.
It is. The purpose of a vaporizer is to turn a potent liquid anesthetic into a precise vapor concentration. We primarily use what are called variable bypass vaporizers.
How does that work, simply?
You have your fresh gas flow coming from the flowmeters. The vaporizer splits this stream. One part goes straight through a channel, that's the bypass. The other part is diverted down into a chamber that contains the liquid anesthetic, like Sevoflurane or Isoflurane.
And it picks up the vapor there.
It gets saturated with vapor, and then it rejoins the bypass gas. The dial on top basically controls that splitting ratio. A higher percentage means more gas goes into the vaporizing chamber.
But there's a physics problem here, isn't there? Evaporation causes cooling.
Correct. It's called the latent heat of vaporization. As the liquid evaporates, it loses heat and the whole thing gets cold. If it gets too cold, it vaporizes less effectively, and the output concentration would drop.
So how do they fix that?
To fix this, vaporizers have automatic temperature compensation. Inside, there's a bimetallic strip, or a special expansion element. As the temperature drops, the strip bends and opens the valve more, allowing more gas into the chamber to compensate for the lower vaporization rate. It keeps the output remarkably constant, regardless of temperature.
What about the pumping effect? I've heard that term.
Yes, that's another important safety consideration. This happens during positive pressure ventilation. When the ventilator pushes a breath in, back pressure can travel up the circuit and into the vaporizer.
And that's bad because...
It can compress gas back into the vaporizing chamber, effectively giving it a double dip of vapor. It transiently increases the concentration delivered, which could potentially overdose the patient. Modern vaporizers use long spiral inlet tubes or internal baffles to prevent this retrograde flow.
We have to mention the outlier, Desflurane, the Texas 6 vaporizer.
Desflurane is the problem child. Its boiling point is 22.8 degrees Celsius.
That's basically room temperature in many parts of India.
Exactly. If you put Desflurane in a normal variable bypass vaporizer, it would boil uncontrollably and you'd give a lethal dose. It would be completely unmanageable.
So how does the Texas 6 vaporizer handle it.
It's a completely different technology. It doesn't use variable bypass at all. It heats the Desflurane liquid to 39 degrees Celsius, creating a pressurized gas at 2 atmospheres. It then injects this pure Desflurane vapor directly into the fresh gas flow using a differential pressure transducer. It's an injector or a blender, not a traditional vaporizer.
And that's why it needs electricity.
That's why it has a power cord and a battery. It needs electricity to heat the sump and run the electronics.
Okay, let's move into Part D, breathing and safety systems. First, the common gas outlet, or CGO.
This is really just the terminal point of the machine's internal piping. It's where the fresh gas flow, the mixture of oxygen, other gases, and vapor, exits the machine to connect to the breathing circuit. It has a standard 22mm outer diameter and a 15mm inner diameter connector.
Now, let's aggregate the safety systems. We've already covered PSS, DIS, and the Eager sequence, but we need to distinguish between the oxygen failure protection device and the hypoxic guard. Students often confuse these two.
This is probably the most common confusion point in the theory paper. So let's be very clear here. The oxygen failure protection device, which is often just called the fail-safe, protects against a failure of supply pressure.
So if the pipeline fails or the tank runs out.
Exactly. It relies on a master and slave relationship. Oxygen pressure is the master. If your oxygen supply pressure drops, usually below about 30 psi, a valve automatically cuts off the flow of nitrous oxide.
So it prevents you from giving 100% nitrous if the oxygen tank runs dry.
Yes, but, and this is the huge caveat, it only detects pressure, not flow.
What does that mean in practice?
Imagine your pipeline is working fine. You have 50 psi of oxygen pressure coming into the machine. But you, the doctor, you reach over and turn the oxygen flow meter knob to 0. The fail-safe valve sees 50 psi of pressure, so it stays open. It will happily allow you to deliver 100% nitrous oxide because the supply pressure is fine. The fail-safe does not protect against user error at the flow meter.
So what does? What protects against that kind of user error?
That is the job of the hypoxic guard, or a proportioning system. This is the mechanical chain link you see on older Omeda machines, the Link 25 system, or pneumatic diaphragms on newer ones. It physically links the oxygen and nitrous knobs.
How does that work?
If you try to turn on the nitrous, the chain grabs the oxygen knob and turns it on too. It mechanically enforces a minimum ratio, usually ensuring you deliver at least 25% oxygen. You physically cannot dial in a hypoxic mixture at the flow meters.
That is a vital distinction. So failsafe guards the supply, hypoxic guard guards the knobs.
Perfectly put. And remember, neither of them protects you against a pipeline crossover.
Yeah.
If the maintenance team accidentally hooks up the nitrogen tank to the oxygen pipe in the wall,
The machine sees pressure, so the failsafe is happy.
and the knobs are turning in ratio, so the hypoxic guard is happy.
But you are killing the patient.
You're killing the patient.
So what is the only thing that detects that kind of catastrophic failure?
The oxygen analyzer, the paramagnetic or galvanic sensor that sits in the breathing circuit near the patient. It is the only device that actually tastes the gas and tells you, warning, there is 0% oxygen in this mix. It's your last and most important line of defense.
Let's touch on the oxygen flush valve, the big emergency button.
It is. It delivers pure oxygen at a massive flow rate, somewhere between 35 to 75 liters per minute, and it completely bypasses the flow meters and the vaporizers.
So its use is for
Rapidly refilling the breathing bag, or, in an emergency, flushing anesthetic agents out of the circuit.
But it has significant risks.
Huge risks. Bare trauma. 75 liters per minute is like a fire hose.
Yeah.
If you press that button while the patient is connected to a ventilator during the inspiratory phase, when the lungs are already full and the valves are closed, you can blow out a lung. You can cause a tension pneumothorax.
So the rule is?
Never, ever press the flush button during inspiration.
Okay. And briefly, the scavenging system.
Its main purpose is environmental safety for the staff and the OT. It collects waste anesthetic gases from the APL valve and the ventilator relief valve and vents them safely outside the operating theater.
Why is that important?
To prevent the OT staff from chronic exposure to waste anesthetics. In early literature, this was linked to health issues like spontaneous abortion and other problems. It can be an active system with a fan or suction, or a passive one.
Okay, Part E, checks and troubleshooting. This is where the rubber really meets the road, the cockpit drill. How do we structure this for an examiner who is watching us?
You need a logical, hands-on sequence. The examiner is watching your hands as much as they are listening to your words. Step 1. Electrical and gas supply. Check the machine is plugged in and turned on. Check the pipeline pressure gauges are reading correctly, around 50-60 psi. Then go to the back, Open the cylinders, check their content gauges.
And then, crucially, close them. Why do we keep coming back to this? Why is closing the cylinder so important?
Two big reasons. First, as we said, to prevent silent depletion if the pipeline pressure fluctuates. But second, if the pipeline fails during the case, you want the low-pressure alarm to sound so you know there is a problem. If the cylinder is left open, it just seamlessly takes over, empties itself without you noticing, and then you have a double failure with no backup.
Got it. Okay, step 2?
Flowmeters. Turn them all on. Watch the bobbins. Do they spin? Do they move smoothly without sticking? Then actively check the hypoxic guard. Turn the oxygen flow to 0, then try to turn on the nitrous. You should see the oxygen knob turn with it. Demonstrate to the examiner that the safety link is functional.
Step 3.
Vaporizers. Check that they are full. Check that the filler caps are tight, and then check the interlock system. Try to turn 2 vaporizers on at the same time. It should be physically impossible.
Step 4. The big one. The low-pressure leak test.
The gold standard here, and the one you must describe, is the negative pressure test, or universal leak test. You attach a special suction bulb to the common gas outlet. You squeeze it to create a vacuum, a negative pressure. And what are you looking for? If the system is sealed, that bulb should stay collapsed for at least 10 seconds, though the official standard is 30. If it reinflates, it means air is being sucked in from somewhere, a loose vaporizer, a cracked flow tube, or a bad seal.
Why a negative pressure test? Why not just pressurize the system and listen for gas leaking out?
Another critical Viva question. Because most modern machines have a check valve near the outlet to prevent backflow from the patient circuit. If you use positive pressure, that check valve closes, and you're only testing the circuit downstream of the valve. You completely miss all the potential internal leaks in the vaporizers and flowmeters. Negative pressure pulls that check valve open and tests the entire internal low-pressure system.
That's a key distinction for the exam. Step 5.
The breathing circuit itself. You perform a 2-bag test. You have 1 bag on the patient end of the circuit acting as a test lung and the reservoir bag on the machine. You pressurize the whole system to about 30 centimeters of water pressure. You check for leaks, and you ensure the APL valve releases pressure correctly when it should.
And finally, the monitors.
Absolutely. Calibrate the oxygen analyzer. It's the most important one. Expose it to room air, it should read 21%. Then flush it with pure oxygen, it should read 100%. If it doesn't read 21% in room air, you need to replace the fuel cell. You do not start the case.
Okay, let's do a quick troubleshooting round. Section 12. Scenario. You are in the middle of a case. The oxygen failure alarm goes off. Your pipeline pressure gauges drop to 0. What is your immediate action plan?
Immediate action 1. Open the emergency oxygen cylinder on the back of the machine. Immediate action 2. You must disconnect the pipeline hose from the wall outlet.
Why disconnect the hose? You've already opened the cylinder. Isn't that enough?
No, because you don't know why the pipeline failed. It could be low pressure, yes, but it could also be contamination. Or the pressure might just be fluctuating. If the pipeline pressure flickers back up above 45 psi for a second, the machine might try to draw from that bad pipeline again because of that pressure gradient we discussed. By disconnecting, you physically isolate your machine and guarantee you are running purely on your clean, known cylinder supply.
And what if the machine itself fails? Let's say the electronics go dark, you smell smoke, or the ventilator just stops cycling.
Do not tinker. Do not try to be a biomedical engineer while the patient is desaturating. You disconnect the patient from the machine completely. Grab the MBU bag, the self-inflating bag, connect it to a separate oxygen source like an auxiliary flow meter on the wall or a separate transport cylinder, and you ventilate manually. Total dissociation from the faulty workstation is the only safe option.
Part F, exam integration. We're almost there. For the diagram in the theory paper, we need to draw this.
Yes, and you need to practice drawing the schematic. 3 boxes. High, intermediate, low. In box 1, high pressure box. Cylinder yoke, its first regulator. In box 2, intermediate, pipeline inlet, dash oxygen flushers via flow control valves. In box 3, the low pressure system, flow meter tubes, vaporizers, Mako CGO. In box 3, the low pressure system, keep it linear, label the check valves, and label the key safety devices like the fail-safe and hypoxic guard.
Okay, let's summarize the Viva traps we've covered throughout this.
Okay, rapid fire.
Does the fail-safe prevent hypoxia? Your answer, no. It only prevents hypoxia caused by low O2 supply pressure, not from incorrect knob settings.
Trap 2.
Where do you read the bobbin? Your answer. Top of the flat bobbin, center of the ball.
Trap 3.
Why is the O2 cylinder green? Your answer, it isn't, not here. It's a black body with white shoulders because we follow the ISO British standard in India.
And the big one, trap 4.
Does the pressure gauge tell you the contents of a nitrous oxide cylinder? Your answer, no, it is a liquefied gas. Only weight can reliably tell you the contents.
Expert, give us the elevator pitch, the summary statement for the student to close out their long answer question.
Okay, here it is. The Boyles machine is an integration of 3 distinct pressure systems designed for redundant safety. The high pressure is contained, the intermediate pressure is the working bridge, and the low pressure is the precise but vulnerable delivery system. Safety is layered and redundant. PIS for connections, regulators for stability, the eager sequence for leaks, interlocks for overdose, and hypoxic guards for mixtures. But the ultimate safety feature is not mechanical. It is the vigilant anesthetist who performs a rigorous and comprehensive pre-use check before every single case.
Outstanding. Now, before we sign off, a final thought for the outro. We've just spent a good amount of time talking about bobbins, springs, chains, and rubber washers. Mechanical things. But if you walk into a high-end OT today, you see digital screens, automated loops, target-controlled infusions.
That is the future, and it's also the risk. We are moving from a world of flow and pressure to a world of algorithms. The modern anesthesia workstation is, in many ways, becoming an iPad on wheels.
So what's the provocation?
My provocation to you, the student, is this. As we automate, do we lose the intuitive physical sense of the machine? When you watch a bobbin spin, you see the flow. It's tangible. When you look at a digital number on a screen, you are trusting a sensor.
And if the screen goes black?
If the screen goes black, or the sensor drifts, or the software glitches, do you understand the underlying pneumatics well enough to bypass the computer and save the patient? Automation should be a tool to aid our understanding, not a replacement for it.
That is a very sobering thought. A machine is only as safe as the human operating it. So, for everyone listening, go grab a piece of paper right now, draw the high, intermediate, and low pressure boxes. Label the components. Do it while this is fresh in your mind.
Good luck with the Gujarat University exams. You have got this.
Thanks for listening to The Deep Dive. We'll see you next time.